Hi everyone, this video is going to be going over examples from quiz 12. And I'm going to start off with some true and false ones. So the first one here says if the boundary of a region is made up of 5 pieces that have points of symmetry, it can always be used to tile the plane. So we've got something that's made up of 5 pieces. And Conway's criterion says if it's made up of 5 pieces, it's got to have 2 pieces that are direct translates of each other. So this one, and I'll give an explanation for these. We'll say false. 5 pieces means we need direct. We need 2 pieces on opposite sides. To be direct translates of each other. Okay. 2 parallel lines of symmetry in a tiling always have the same reflective symmetry. So we saw an example of this here where, yes, it is possible that we have parallel lines that are not unique, right? They have the same symmetry. But looking at this square tiling here, just because they're parallel, they have to also go through the shape in a different way. So we can say this is also false. They can have different symmetries if they go through the shapes in a unique way. Okay, next one. If a tiling in the plane has translational symmetry, so what that means is that it's periodic, right? So if we have a periodic tiling, then the only points of symmetry that are possible are 2 centers, 3 centers, 5 centers, and 6 centers. So we'll say false. We'll say the actual list. So this is a theorem from your textbook. The actual list is it's got to be a 2 center, 3 center, 4 center, or a 6 center. Right? Those are actually the only possible list of centers that we can have if the plane has, or if that pattern has a periodic or translational symmetry. Okay, when classifying centers, we choose the smallest angle of rotation. So this is something that's using a phrasing that I think can make this complicated, but I'll get into it very quickly here. Let's look at these ones here. So we saw that point A is a 2 center because it only rotates every 180 degrees, and point B is a 4 center because we get every 90 degrees on there, we get a shape back. So what this is getting at is if we look at the increments of these symmetries, right? This one has 180 degrees, so we would call it a 2 center. This one, every 90 degrees, so we would call it a 4 center. What this is trying to tell you is that point B is not considered a 2 center, right? When we're naming point B, it's true that every 180 degrees we get a rotational symmetry, but basically we use the highest number that we can for this measurement here. So if something was a 2 center and a 3 center, we would want to use 6 center for that. But yeah, looking at the actual example here, when classifying centers, we choose the smallest angle of rotation. We'll say true. This angle is the increment between rotational symmetries. And we could say even furthermore that it's the increment between the rotational symmetries and if something, or if a point is a 2-center and a 4-center, we only call it a 4-center. Using the smallest angle, 90 degrees. Okay, so yeah, I think mostly you just kind of want to memorize this statement as being true, right? We're using the smallest increment. That's what gives us the correct name for these things. Okay. Next up, we've got the letter B has exactly one line of symmetry. So not this letter B that they've actually got here, but they're talking about this kind of perfect letter B here. Yeah, that has one line of symmetry going through it like that. So we would say true. Conway's criterion can be used to determine if a region can be used to tile the plane. True. This is the use for Conway's criterion. Okay. A non-square rectangle has exactly 2 lines of symmetry. Go ahead and draw one here. All right, so those 2 lines of symmetry are going to look like that. Perfect. And again, we're not talking about tiling. We're just talking about that particular shape there. Something like this would not count. So yeah, just the horizontal and vertical ones, we'll say true for that one. So the diagonals will not give symmetry. 2 parallel lines of symmetry in a tiling always have the same reflective symmetry. That's a repeat of that last one. So we'll say false there. If the tiling in the plane has a translational symmetry, the only ones possible are those 3. So we'll say false. I mentioned last time the actual list is 2, 3, 4, or 6. Okay. These are more about the section 5.3. So the sum of the angles in a Penrose dart is 360 degrees. Yeah, it's 4-sided. True, Penrose darts are 4-sided. Polygons. And we'll be nice to Mr. Penrose there. No Penrose tiling has translational symmetry. This is true. So that translational symmetry, that's what we would make something have a periodic tiling. So yeah, true. Penrose tilings are non-periodic. Okay, a golden diamond can only be created with type 2 golden triangles. Not true. We can make them with type 1 and type 2, those would both be considered golden diamonds there. Okay. It is impossible to tile the plane with only Penrose darts. Now, they're trying to trick us here a little bit. So they're saying they're maybe kind of calling into question the Penrose tiling being non-periodic, so it's impossible. But remember, Penrose darts are just a four-sided polygon. So any four-sided polygon can be used to tile the plane. We saw that a couple sections ago, so yeah, that's totally fine. Two type 2 golden triangles are used to create Penrose kites, false. Kites are made of type 1. And that would make this one wrong as well. Two golden triangles. Okay. Semi-regular tilings are periodic. False. Wait. Sorry, I thought it said Penrose tilings there for a second. This is true. Remember, every tiling that we've looked at that's not a Penrose tiling is periodic tiling. So that one's just true. Golden diamond can be created using both a Penrose kite and dart. This is false. They're made using the golden triangles. Okay. The sum of the angles in a Penrose dart is 180 degrees. This is false. A dart's interior angles are 360. Since it's a four-gon, right? Four-sided polygon. Okay. Let's get into the Conway criterion type of questions. So for these ones, there's two types of problems in here. One of them is going to be giving you the pieces exactly as they are, right? So you have to use these pieces in exactly the way that they're arranged currently. And then this other type is you're free to kind of pick where to put the pieces on there. Anyway, let's look at this first one here. So they've given you the pieces. Which of the following has its boundary properly divided into pieces with allowable symmetries according to Conway criterion for tiling the plane? Note each color denotes one boundary piece, and if there's ever a color, so this would be one piece here, right, in the pink there. But if you saw pink over here as well, then that would be a different piece. That's what they're saying. Okay, so this is 1, 2, 3, 4 pieces. So 4 pieces. Does this piece have rotational symmetry? Yes, if we rotate that 180 degrees, that will fit back into itself. So that's good. This piece, any straight line has rotational symmetry. Any straight line has rotational symmetry. So I'll just maybe check these off. I'll say rotational symmetry. Yes. 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 And no. If I rotate this 180 degrees, that will not fit back into itself. Part of it will, right? But again, we need to take the pieces exactly as they are. So we'll say no. So that one's not going to work. This one here, so we've got 1, 2, 3, 4, 5, 6 pieces here. Let's think about if any of these are translates of each other on opposite sides. Let's see, this one, no. These two. These two appear to be opposite sides and are translates of each other. So and you can kind of use the grid to say it's up 3 over 1, up 3 over 1. So yeah, these two are fine. And then every remaining piece is a straight line. So they all have rotational symmetry. These are on opposite sides of each other. So we could say, yes, that satisfies Conway's criterion. Okay, this next one here, let's see, this piece and this piece. So we've got 1, 2, 3, 4 pieces. So we're not looking for translates here. We're just looking for rotational symmetry. These are both straight lines, but this thing as an entire piece here, right? This whole piece here and this whole piece here do not have rotational symmetry. So we would say no, not for this one. Okay. This one's a little more interesting. We can actually look at the, we can decide where the pieces go on here in a more interactive way. So just looking at the complicated nature of this piece here, my thought is this needs to be broken up into 5 or 6 pieces, right? So I'm going to start looking in this piece for things that have translational symmetry. So maybe this and this look like have rotation, or sorry, are translates of each other. I don't see any pieces that kind of look like I could flip them over and get the same piece back, but I do see a repeat of this pattern here. So I'm going to call this one and this one. I'm going to work with those and see if those ones can be direct translates of each other and see if I can break them down into enough pieces. So I'll just kind of break it down naturally as best I can. 1, 2, 3, 4, 5. So this one, looking at it, I've got 1, 2 pieces that are direct translates of each other. 3, 4, 5, 6, 7 pieces. And I don't see any way, so I would need to combine something over here so that they would be on opposite sides. I don't see any way to combine these to make something that has rotational symmetry on here. So I'm going to say we've got 7 pieces and no way to combine them to make rotational symmetry on these. So I'm going to say no for that one. This one here, I've got an eye for these sorts of things. I am looking at this piece here, and I say this piece has rotational symmetry. I can take that even further, right? Because the other possibility is that I have, 6 pieces on here. I'm going to take this even further and say this entire thing here, if I take that shape, here I'll even try to show that to you. All right, if I take that entire shape and I rotate it 180 degrees, that in fact does fit back into that spot there. All right. So I feel comfortable calling that entire thing one piece, and then the rest of it's very straightforward to break down. So that's going to be 1, 2, 3, 4 pieces. Great, yes. Great. This one here, again, another complicated shape. So I think I'm going to need it to be have some direct translates over here. I could think about making these two direct translates of each other, but I am going to have this extra piece left over here. I see some pieces that I can make into direct translates of each other right here. But looking at the remaining pieces, everything's going to be working out really nicely for me. Right. I've got two pieces that are direct translates of each other. So this piece and this piece are direct translates of each other. All the remaining pieces have rotational symmetry, and these two are in fact on opposite sides of each other. So everything's working out great for that one. So I'm going to call that another yes. Just practice with these, right? Recognize that there's two different types of problems. One where they show you the pieces and you tell them yes or no, and then another type where you're given the shapes and need to kind of come up with the pieces. But do a couple of these, you'll kind of see the rotational symmetry patterns that they come up with for you. Okay. This one here, this is asking about how many lines of, say, how many unique lines tree in the tiling pattern. So let's see how many we can find here. I'm going to go with 1, 2, 3. So those ones are pretty easy to find. But there's also these ones over here. So those go through the hexagon, but there's also these ones that go through the triangles. Right. So none of them are parallel to each other, but I count 1, 2, 3, 4, 5, 6 of those. Right, 6 lines. Okay. This next one here. Now, we're looking for lines of symmetry, not rotational symmetry. So there's a couple things I'm going to have to exclude here, but let's see. So if I take a line like this, maybe this is a good one to do. But this is, at least for the hexagon, it's making some nice symmetry on here. But I can see already that, for example, this hexagon over here, if I try to translate that over here, I would expect to see a hexagon over on this side over there. So that's not going to work. And I'll try to put one through here that's sort of reflecting these triangles, but I'm seeing another problem already where this hexagon isn't translated properly. So I'm just going to keep attempting some things here, right? This maybe, no, it looks like it works for a little bit, right? At least locally, this is translated or mirrored over here, mirrored over here, mirrored over here, but this hexagon does not mirrored over here. So as it turns out, none of these lines of symmetry that I can draw are going to work. So this one actually has 0 lines of symmetry. And that's possible, right? Even in something that's, nicely arranged like this, it's possible to have 0 lines of symmetry. We will find all kinds of points of symmetry in this one, though. This one is one that you could definitely expect to see the same pattern repeated. Okay. So for this one here, these are about rotational symmetry, so points of symmetry. And it says a portion of the, oh, there it is. It says a portion of a semi-regular tiling is shown below. Assume the pattern continues beyond the portion shown. And then we'll evaluate these statements one by one. So the first one says each square is a 2-center. So again, a 2-center is something that if you rotate it 180 degrees, then you are going to get that same pattern back. So if I take this pattern, I'm actually going to show this over in Publisher so I can show you what this looks like rotated. Okay, so for this tiling pattern, I'm just going to look at this particular square right here. But if I take that and I rotate it, sorry, I just need to crop that a little bit to rotate the way I wanted to. So if I look at this pattern here and I rotate it 180 degrees, I do get that same pattern back. So in that sense, it's a 2-center, but the statement's actually false because if I rotate it 90 degrees, I also get that same pattern back, 180 and 270 degrees. I also get that same pattern back. So the actual statement that I want to make about this, I had to move it back to the OneNote, is that it's not a 2-center, but each square is instead a 4-center on here. So I'll go ahead and type that in. I suppose I'll need to draw it in. False, it's actually a 4-center. Okay. A 2-center is the midpoint between is at the midpoint of the common edge between 2 adjacent triangles. So we'll have to do a little bit of work translating what they mean here. So this is what they're talking about here. If I rotate this 90 degrees, I don't get anything back. I don't get the same pattern back. But if I rotate around this point here, 180 degrees, I should get these squares are certainly in the right position. Looks like everything else is in the right position, so I'll say that this one is true. So, and they're talking about the orange point there. I'm just going to clean this up a little bit. Okay. There is not a 2-center at the midpoint of the common edge between a triangle and a square. Okay, so let's look at we'll label these as black points here. So the common edge between a triangle and a square. Well, if I rotate this 180 degrees, I'm going to get a triangle over here and a square over here. So I would say that's going to be true every time, right? Let me just double check here. Common edge between a triangle and a square. Yeah, that's going to be a true statement. There is not a triangle and square with switch places. And that's the black point there. Okay. This next one here, I really like this tiling pattern. I'm actually going to put that up, so just in case you don't see them in the practice problems or the quizzes, I'm just going to put up all these sort of tiling patterns that are from different buildings around the world, so you can take a look at those. But okay, point A. So they're describing this point here is a 3 center, but not a 6 center. So in the middle of these 6 pointed stars here, we should be able to rotate them. So a 3 center means that every 120 degrees, so at 120, 240, and 360, we get that same pattern back. I've actually got a little demo of that here in Publisher, so I'm going to show that real quick. Okay, so I've got the same pattern here. I'm actually going to call this, so I know this is point A in the middle of the 6-pointed star here, but I'm going to choose this middlemost 6-pointed star to look at for just a second here. I'm going to crop it. Just a tiny bit more to get the effect that I'm looking for. Okay, so this one here, if I take this as the center point of it and I rotate it, I do get that same pattern back 1, 2, and then back to the original position 3 times. So I'm kind of looking at these, white little wings on the side here. So again, I get that lining up 1, 2, 3 times there, and we're ignoring the colors of things on this, but notice that I don't get that same pattern back 6 times, right? And you can kind of see that if you look at the amount of spokes on this wheel, right? I think about it. I can go back to OneNote now. If I look at the sort of spokes on this wheel, right, just kind of extend, find a little piece of that tiling, see what that produces. So looking at this, I get, let's say 3 center, not a 6 center. Let's say true. Look at the green outline. It's got 3 spokes on the wheel there. Okay. Next one, point B is a 3 center, but not a 6 center. Exact same, right? Exact same sort of logic with that one. So I just want to make sure, I've got 3 spokes here, but I just want to kind of make sure that extending that pattern works. I've got these 6-pointed stars here. Those are all going to have 3-pointed symmetry. Yeah. So these hexagons have maybe that would be a 6. If I just look at these hexagons, I would get 6 of those to line up, but the whole thing has to line up, and I would say that that's true as well. Okay, point C is a 6 center. I don't even think this is a point of symmetry at all, right? I've got a 6-point star up here. I've got this wing down here. So I'll say false, not a point of symmetry. Okay. I think that was enough for, we already looked at some points of symmetry, or sorry, lines of symmetry problem. This one here, this is another situation where we've got 0 lines of symmetry. If you try to draw any lines around there, you're going to get nothing but rotational symmetry. But I just wanted to show that that was another example from the actual tiles. Last problem I want to go over, this is finding the length of some sides here, but also show you an area problem as well. So let's see, this is a Penrose kite, so it says if BC is equal to 6, then what is the length of AD? So just remember that this is made up of 2 golden triangles here, right? So those 2 golden triangles are type 1. If this is 6, this is 6, this is going to be 6 times phi, or 6 times phi. So the length of AD, this is kind of a mercifully easy problem. 6 times 1.618 is going to be equal to 9.708. Okay. So AD is going to be 9.708. If you're asked to find the area so we'll say what is the, I'll show you how to do that. What is the area of the kite? Finding the perimeter should be fairly easy, right? Just adding up these pieces here. But again, this is 6, this is 6, this is 9.708, this is 9.708. And the way that I would handle this is I would break this up into 1, 2, 3, 4 right triangles. So if I just kind of take one of those right triangles, I'm going to take this farthest one over here. Right. So I'll just kind of make a copy of that over here. That right triangle is going to have a side of, so this is 6 divided by 3, right? Because I'm cutting this in half. So 2 over here and 9.708 over here. So I can use that to say that 2 squared plus b squared, call this b, is equal to 9.708 squared. B squared is going to be equal to 9.708 squared minus 4. So that's going to be 90.245. And square rooting that, get 9.5. Okay, so this is going to be 9.5. The area of a right triangle is equal to 1/2 base times height So in this case, it's going to be 1/2. This is my, well, I'll call this my height. This is my base here, just to keep those letters the same, but basically the two sides that aren't the hypotenuse there. So 1/2 times 9.5 times 2. Okay. So this is just going to be 9.5, right? 1/2 times 2. Perfect. Oh, oh shoot, I messed this up. I don't know why I divided by 3 there. Very silly of me. I knew it was too good to be true. This is 6 divided by 2, which is 3, of course, right? If this measurement here is 6, this is 3, and this is 3. Sorry, so it's actually 3 squared plus b squared is equal to 9.708. 9.708 squared minus 9. That's going to give me 85.245. So b is going to be equal to 9.23. Yeah. Okay, so 9.23. The area of that right triangle is going to be 1/2 times the base, which is 9.23, times the height, which is 3. So we get 0.5 times, or 9.8, or 9.23 times 3. So that's going to give me 13.85. And I used the actual. I didn't use 9.23. I used the actual square root of this value here. So 13.825, the last step is to say that the area of the whole kite is not just this 13.85, but 4 times the area of the right triangle. So that's going to be 4 times 13.85. Which is going to be 55.4. Okay. I believe that's everything I wanted to go over. I think the Conway's criterion ones are just going to take some practice, and these lines of symmetry, you might even see there's not too many semi-regular tilings, but just kind of keep asking yourself, have I really checked everything? Because it's a lot easier to miss them than it is to put too many in there. Okay, that's all for this video. Email me if you have any questions, and I'll see you in class on Monday.